Hello, and welcome to our demo on the slam valve motor. Today, we'll be using the slam valve motor to generate electricity. This is grid-tied power. We'll be shoving electricity back into the grid and spinning an electric meter backwards. It is April the 9th, 2010, and we're looking at an early demo of the Mark II slam valve motor head. What we have here was at one time a Harbor Freight air compressor. We removed the top and added our own custom slam valve head. This is the Mark II version. This is improved over the Mark I. We'll show you the Mark I in a moment. The slam valve motor has a belt drive. The belt is 10.5 inches. Behind it is a flywheel. We add a little extra momentum to smooth out the power for the generator. And it drives an ordinary induction motor with a 3.5-inch pulley. And the induction motor is an 1800 RPM half horsepower motor. And today it will become a generator. Because of the pulley sizes, the slam valve motor will be running at 600 RPM, which is 10 rotations per second. Compressed air comes in through the copper pipe here, and exhaust comes out through these ports on the side. You'll notice there are no plumbing connections to the bottom. So, should you need to replace your piston, you don't need to replumb. All the bolts are accessible on the top, and bolts to hold the air compressor down, and for $100 you can have yourself a new piston. This is the Mark I version of the slam valve head. It's very similar to the Mark II, and what you see here is two anodized plates with these cavities and these stainless steel springs. And the springs are curved and they sit over a hole in the cavity, and under a certain time they will seal, cover the hole, and at certain times they spring up and allow gas to pass through. These are control rods. These set the speed. They're actuated from the top. We use gaskets to seal this version. The new one needs no gaskets. That's one of our improvements. There's a manifold here to lead the plumbing in and out, and it mounts on top of a Harbor Freight air compressor like this one. Now on with the demo. The induction motor is going over to this electrical panel here. On the electrical panel we have a kilowatt. The kilowatt is just a digital device for reading power, and right now it's set for watts. It's reading 0 because there's nothing plugged into it. And this is in series with this watt-hour meter, which is similar to what's on the side of your house. The interesting thing about the kilowatt is it reads pretty accurately, but it doesn't have a sign. So once we start generating power, you won't know that from power consumed without looking at the disk on this watt-hour meter. When we're consuming power, the disk will be turning to the right, and when we're generating power, the disk will be turning to the left. And you'll see that. And we'll watch pressure on this gauge, and this shows us air consumed. We'll compute efficiency from this. And you can see this is an 8-gallon tank, and this is the plug for the air compressor. We're not running the air compressor right now, so we'll be running entirely off stored air from the tank. I'm going to show you an overview, and then we'll run one more demo where we'll zoom in and see the pressure and power consumed. And from this we can compute efficiency. So, without further ado, first we're going to start this as start the induction motor to start the process going, and we'll see power consumed. And we turn on the compressed air, you'll see power being generated. Okay. You can see we are consuming about 250 watts, and on the watt-hour meter there's a mark on top of the wheel, and you'll see that going to the right. You see we are consuming power. The disk is turning to the right. We'll be generating power soon. I'll show you the motor itself. Spinning. This is a synchronous system. It's a synchronous motor. Well, it's an induction motor, lags a little from a synchronous motor. But you see the beat pattern from the sampling of the camera makes it look like it's spinning very slowly, but it's really spinning 10 rotations per second. Okay. Oh, also like you to observe, at the exhaust port we see no cloud. We'll be seeing a cloud when we turn it on because this is an expansion motor, and one thing about an expansion motor is it produces a cold output gas. And the cold output forms a cloud at the exhaust port during part of the process. So, let's see some power being generated. I'll turn on the air as soon as it just goes by. There's power being generated. 138 watts. And that's part one. Next time we'll see this again with just the instruments. And let's see that again, this time watching just the instruments. You see we're drawing about 250 watts. The tank is fully charged at 112 psi. And we are consuming power. Watch the mark go by. And now we're generating power.
Next, we'd like to show you how to go from the instruments you just saw to power and efficiency. First, we record the pressure of the compressed air tank versus time. We convert to pressure absolute. Then we take the slope of that line, multiply by the tank volume, divided by the absolute pressure, and that gives us flow rate. Within the motor, this flow rate expands without adding heat, adiabatic expansion, to produce a cold gas at the atmospheric pressure. Next, we take the flow rate at the intake pressure, multiply it by the pressure to get power. That's the power of the intake stroke, which is between 400 and 500 watts. Next, we allow that gas to expand. As it expands, the pressure drops, and as it does so, it produces work. This is between 600 and 350 watts, which is, during part of the experiment, that's actually more than the intake stroke power. Next, we have to get the exhaust out of the motor. This is a negative. That's just the flow rate at the exhaust pressure times the ambient pressure. We add up the three pieces, intake plus expansion minus exhaust power, and we get the total power that would come out of an ideal motor that consumed this much gas. Next, we look at the induction motor. We see that it draws 120 watts when it's not loaded. We see that it consumes 5.3 amps at 120 volts when it's producing 1/2 horsepower. Between these, we get the marginal efficiency. That's the change in shaft power divided by the change in electrical power. And we get the friction from the fact that the unit draws 250 watts when it's driving the piston assembly and the belt. So there's 90 watts of friction. We take the kilowatt and we plot the output of the kilowatt versus time. And because it jumps around a little bit, we do a little smoothing on this. We feed that back into the motor equation, and we get the shaft power that it would take to drive this induction motor to produce that much electricity. You may notice the efficiency is lower than 50% during a lot of this experiment, and that's actually about the going rate for low-cost generators. Gasoline-powered generators at the hardware store, if you look at the output power and divide it by the horsepower of the gasoline engine, you'll find 50% is about right. Now, we take the shaft power that it took to generate this much electricity and divide it by how much energy would have come out of an ideal adiabatic expansion cycle that consumed this much gas, and we get the total efficiency. The total efficiency is about 80% of an ideal adiabatic expansion cycle. Thank you for your time. Please come visit us at slamvalvemotor.com.